solve, how do you solve this right here? Elimination substitution. Multiply the top one times -3, which gives you -3x minus 6y equals -21. Then group your two equations together. So you get -11y is equal to -11. So y is equal to 1. From there, I would substitute it back in right here. So then x plus 2 times 1 is equal to 7. So you get 2. If you move it over, it becomes -2, and you get x is equal to 5. What that finds for you is a point. That point is the point of intersection. You have two lines, graph x and y both to the first power are equations of lines. So your lines will intersect at this particular point. Now, the only time you don't get a point of intersection is if the lines are parallel and the slopes would be the same. But that's not the case here. So you've done this. Because the next thing we want to talk about is we're going to look at what you can do if you have fractional equations. Let's get rid of the fractions. I don't know how many people really like working with fractions. So we're going to look at fractional equations and how to change it so that you just have integers that you're dealing with instead of rational numbers. We're going to look at radical equations, and then we're also going to, the reason you had that for a bell ringer is because you're going to look at a system of 3 linear equations next. So hopefully you got elimination substitution down, because let me advance forward here a minute. And look at what you get to look forward to. You talk about x, y, and z. You actually have an x, y, and z axis. That's when you get into 3-dimensional. So, and I'm missing one of my meter sticks up here. I don't see one. You talk about your x, y axis, and z is like this, coming out at you. So it's a 3D chart. So you have x, y, z. So a point, you would go x, y, z. Forward or backwards. When you're looking up here, you're still looking at a point of intersection. But what you have? X, Y, Z. Nope, you're still going to be doing elimination substitution. There's going to be multiple ways to go about solving that. But I just wanted to refresh elimination substitution with 2 variables before we got to 3. But before we get to that, what happens when you get to something like this one? And I say, all right, solve. That's equation of 2 lines. And I want to know, what is their intersection point? Oh, you got to multiply by something to eliminate, or you want these coefficients to be opposites or additive inverses, then it becomes more difficult. So to help with that, we have a process where we're going to work with fractional equations. And we're going to simplify those fractional equations so that we have integers involved. We don't have fractions anymore. If you have an equal sign, that's the key thing. You can't do it if there's not an equal sign. If you have an equal sign, you can eliminate the denominator. The way you can eliminate the denominator is multiply both sides of the equation, which is legal in algebra. Multiply both sides of the equation by the common denominator. What's going to be the common denominator between 7, x plus 2, and 3? 21, the quantity x plus 2. I would not distribute that through and say it's going to be 21x plus 42. So I want to take both sides of the equation times that common denominator of 21 times the quantity x plus 2. Which you can do that, right? If you do that to the left-hand side, what are you going to have to use? Distributive property. So using the distributive property, I'm going to set it up like that. Now I'm multiplying fractions, and when I'm multiplying fractions, you can think of this as being over 1, but you can reduce a denominator with the numerator. So you get 3. So what is 3 times 4? 12 times x plus 2.
Do you want to write that out?
That I would write out. What happened? The first term, I got rid of the fraction, right?
Yeah.
What about the next term? If I look at the next term, I can get rid of the x plus 2. That actually cancels. So you're taking 21 times 3, which is 63. If we look at the last fraction or the last term, if you look on the right-hand side of the equal sign, 3 goes into 21 7 times, and you end up with 35 times the quantity x plus 2. You got rid of the fractions. Does this look easier to solve than what we started with? To solve, what are you going to need to do? Distributive property. So you get 12x plus 24 plus 63 is equal to 35x plus 70. So 12x plus 87 is equal to 35x plus 70. You can move the 12x over, move the 70 over, and you get 17 is equal to, I kind of made that messy there, 35 minus 12 is 23x. Last step, divide by 23. So x ends up being a fraction, not a very pretty fraction or anything like that. But I do think that it's easier to solve by getting that common denominator and eliminating the fractions. Try this one. Okay, so the common denominator is 6 times the quantity x minus 4. This time I'm going to put it towards the back now that you understand where it's coming from. You just multiply every single or every single term times that, because then I think it's going to help with some mistakes that I saw. So when you do that, 3 goes into 6 2 times, and when I write it behind the actual term, I think you see that this becomes 10. So you would have 10 times the quantity x minus 4 minus the x minus 4's cancel, and you just get 6 and 2, which is 12. And 2 goes into 6 3 times, so you get 3 times the quantity x minus 4. You distribute 10x minus 40 minus 12, 3x minus 12. So 10x minus 52 is equal to 3x minus 12. Yep, you take the 5 times the 2. So you subtract 3x, and you're going to add 52. So 7x is equal to 40, and if you divide, you get 47s. Question? All right. Here's how you're going to apply it. You have these 2 lines, and you want to look for their intersection point. Those 2 equations are not very nice to work with, but I do know that that top equation, I can get rid of the fractions. What's the common denominator? 35. So I'm going to take this times 35, take your second term times 35, and take the right-hand side of the equation times 35. When you do that, 7 goes into 35, 5 times, and you get 15x. 5 goes into 35, 7 times, and you get 14y. And remember what happens when you multiply by 11? We separate the 2 digits and add them together to put the middle value, so it's 385. 35 times 11 is 385. That helps the top equation. What do you do to the bottom equation? Move a decimal point over or multiply by 100. One more. Move it over 2 places to give you 3x. Move it over 2 places to give you 20y. I get my sign correct. And move it over 2 places to give you negative 37. Now what can you do with that? Yep, you would do elimination substitution from there. So if I take that bottom equation, I don't know why it does that. Take that bottom equation times negative 5, the top equation, 15x plus 14y equals 385. The bottom equation becomes negative 15x plus 100y is equal to, I think, 185.
Yeah.
All right, this drops out. 114y is equal to, are all my signs correct?
Yes.
Okay. 570. Is that times 5? 114 times 5?
Yeah.
27, 5. 570. So when you divide by 114, you get y is equal to 5. Are you done yet? No.
Okay.
You have to put that back into one of the equations. You could go back into the original equations if you want, but you have fractions involved. The top one wouldn't be so bad to insert it in, just because when you take 2/5 times 5, those 5s are going to cancel. So 3/7 x is equal to 9. And then you divide by 3/7. And if you divide by 3/7, you keep, change, flip, and these cancel to give you 21. Now, if you don't want to do that, are you going to get the same thing if you choose one of these 2 equations to put y is equal to 5 in? Yeah, doesn't matter which one. No, which one would you pick? Oh, really? I chose the bottom one because what? Smaller numbers is why I would pick it. So if I put it in the bottom, sorry, I'm standing in front of it, you get 3x minus 20, and y had a value of 5 equals negative 37. So 3x minus 100 equals negative 37. So you're going to add 100. So 3x is equal to 63, and when you divide, you're back to x is equal to 21. So we have that intersection point. You could say x is 21, y is 5. You could say the intersection point between them is the coordinate point, 21, 5. All means the same thing. I'm not quite for sure. Lindsay has done some of these in college algebra, and I don't remember if she just says x is something, y is something, or if they're making them stated as a coordinate point. But you are finding the point of intersection when you do elimination substitution.
Would the coordinate point just be like the same as row?
Probably, yep. And you can still do it when you talk about x, y, z. You put x, comma, y, comma, z. Still shown as a point. Another question? See, that trick of getting rid of fractions works nice.
What happens if you take 11 times 3 base 100?
Then you start and separate. It's kind of the same process, except for you just start and it would be, I don't know,
Like 113,
3, 1, and then you come up with that value. Just if you were to take, because of this, look at the pattern. You take 113 times 11. You're going to get 113 the first time when you take it times that. And then you put a 0 down, and then you shift everything over one spot. So you write your 3 down, you put your 1 down, and in between there is going to be a 4. But then the next spot you have a 1. So it turns into a 2, and then you get your 1 in the front. The same thing. Okay, what happens when you have radicals within an equation and you're trying to solve? The inverse operations, you have multiplication and division, addition and subtraction. What about a power? The inverse operation is a root. So if you have a root, the inverse operation is a power. So to solve this type of problem that's up on the board, it is the cube root. But as you look at it, the first thing you want to do is you want to isolate that radical. So to isolate the radical, I would move the 2 over to the other side. So you're going to get the cube root of x minus is equal to 4. How do you get rid of the cube? Because now your cube root, sorry, I just said it. Now to get rid of your cube root, what would you have to do? Cube it. Plug this in. All right, so you cube it. What is 4 cubed? 64. So if you finish the problem to get rid of the root, you raise it to the power. And on the left-hand side, you're just going to get x minus 5. The right-hand side, you get 64, and as a final step, you would add 5. So you get x is equal to 69. When you solve these types of problems, you have to check yourself, because there is a possibility it could give you an imaginary number underneath the radical sign or something. So put 69 back in. What is 69 minus 5? 64. What's the cube root of 64? 4. What's 4 minus 2? 2. So that works. There's your answer. You need to check for, they call them extraneous solutions. So just don't, once you solve, you want to put it back in and see if it gives you a correct solution. But what happens when you have 2 radicals involved? I do want to caution you of something. Here's the common mistake people make. What they want to do is they want to square both sides. You get rid of a square root by squaring, right? But here's where you go wrong when you square both sides. What happens if you square the left-hand side? Does it just leave you with something like this? It does not. That's where people make the mistake. And I caution you about doing that as a procedure. If you were to square the left-hand side, when you square the square root plus a square root, you're doing this. The square root of x minus 48 plus the square root of x. Squaring it means you take it times itself, right? And to do that, you have to FOIL. And if you FOIL, what happens when you multiply the first times each other? You get x minus 48. When the radicands are the same, it just gets rid of the radical, the root. But what happens when you multiply the outer? You get something ugly like that. Then you multiply the inner together and you're going to get that same ugly thing again. And you multiply the last together and you get plus x. 8 squared is 64. Did that get you any place? Well, you can group these two together. You could work with some of that stuff. But I think there's an easier process. If you want to come back to this one, I can show you how to do it. But I want to show you a different procedure first that I think is going to make it less complicated than this stuff that I'm erasing right here. Because that gets pretty confusing when you get factors underneath your radicals. But that's what people want to do. They just want to square both sides and then say that gets rid of it. But it doesn't just get rid of, it doesn't just get rid of the radicals completely. You're still going to be left with one. Okay, so here's the procedure we're going to do. Before we looked for the complicated radical, because I only had one radical. Complicated because there was more than one term underneath. So we're going to look for that, which occurs right here, and we're going to isolate that by moving radical x over to the other side. When you do that, you are left with the square root of x minus 48. That is equal to 8 minus radical x. Now that you have a radical isolated, how do you get rid of that? Not divide. How do you get rid of a root? Square it. So I'm going to square both sides. And when I square the right-hand side, you are going to have to take 8 minus radical x times 8 minus radical x. The left-hand side, when you square it, what are you left with? X minus 48. The right-hand side, you FOIL. 8 times 8 is 64. What is 8 times negative radical x? Negative 8 radical x. What about the inner? Negative 8 radical x. What about the last? Negative times negative is a positive. What's radical x times radical x? No, it's just x. The value's under, it's like the square root of 3 times the square root of 3 is just 3. So now you have x minus 48 is equal to 64 minus 16 radical x plus x. What happens when you move this x over to the other side? No, you're subtracting it. So when you subtract it, what happens? Cancels out. Now, does this look better? Yeah, that looks a lot better than the square root of x times the quantity x minus 48. So let's move the 64 over. We're going to isolate this term right here. We want to isolate the radical. So we're going to move 64 over by adding it. And if you add, what are you going to get?
No, 16. Sorry.
Yeah. I was going the other way. I was going to say 26.
I'm pretty sure you're
Oh, she did.
Oh, yeah. It's 64 minus 4. Oh, subtract it. There we go, Landon. See, and somebody said, I am so confused. I didn't hear you. I'm sorry. Sorry, Wilson. Now what do you do? Divide by negative 16.
12.
7. Is it 7? 16 times 7. Now what do you do? How do you get rid of the square root? You square both sides, so you end up with 7 squared is 49. Check yourself.
Yeah, I still have a question.
Just a minute. Check yourself. What's 49 minus 48? 1. The square root of 1 is 1. And then you have the square root of 49, which is 7. Does that equal 8? Yes, it does. So your answer is x is equal to 49.
Okay, can't we just leave the radical x over there and just take it to the second exponent on the left side?
You can't just do something to a term.
Oh, you see it too.
You have to do it to
Well, no,
both
could you
sides
do-
of an equation.
But like, so you know we have x minus 48.
Are you talking about the
radicals.
blue right here?
Yeah, can't you just have plus radical x and that also to the second power, but they're just like separate? You can't. y.
You can't just say a plus radical x over here?
No, because like, all right. So you know how you have the x minus 48?
Yes.
You have that to the second power. Can you just do that the same thing to the radical x?
You can't just put a value underneath there, no.
No, like I'm saying, like how you have this, and there. Can you just go there, and there, and then?
No. Because that would be the same thing as squaring both sides and you just say you get rid of it. Here. Square root of 49 minus 13 plus the square root of 9. Okay, what's 49 minus 13? 36. The square root of 36 is 6. The square root of 9 is 3, which would make this 9. That's a true statement, right? Okay, the question was, can't I just do that? When you square something, squaring is not just, if I were to square this side, when you square something, you take it times itself. You don't just take the exponent and distribute the exponent through. You square it by taking it times itself. So you have to multiply this times that same thing. You have to take what's in purple here in the brackets and take it times itself. If not, just showing you, if I were to do that, if I take the square of that, I get 49 minus 13 plus 9 equals 81. Is that true?
No.
No. So it does not work. You have to do the FOIL process when you have more than one term there. Does that explain it?
Yeah.
Okay. Huh? I know, and that's where people usually make a mistake of trying to square something. All right, here's one for you to try. To do. To accomplish, to tackle. I don't know. What adjective sounds the best? Maybe it's a verb. X minus 7 plus the square root of x is equal to 7. You could take the left-hand side times itself. But then you're going to FOIL with radicals in all 4 positions.
Wait, why? Because
the most complicated part, I would say, is going to be this right here, right? There's the complicated radical. So I would move this radical over to the other side. When you move it to the other side, you have to subtract it. Did we at least get that far?
Yes.
So you have the square root of x minus 7 is equal to 7 minus the square root of x. Now if I focus just on the left-hand side, I have a square root. That's it. How do you get rid of a square root? You square it. So I'm going to take this side and square it, and then I have to square the other side. He wasn't saying that. He was saying just square it up here in the green. You can't do that in the green because you move the radical x over the other side, and it's not being squared if that's the first thing you do. In the blue. If you square it in the green, yeah, this is by itself. You're missing squaring that right there. You come in during study hall 7th hour, or better yet, you come in after school and I will explain. Well, I know. Like your great grandfather was doing that. All right, we square both sides. What happens if you square both sides? The left-hand side becomes what? X minus 7. If you square the right-hand side, you got to take it times itself, and you have to FOIL. So if you FOIL, you multiply the first together, and you get 49. The outer is negative 7 radical x. The inner is negative 7 radical x. And the last is positive x. Square both sides. What you do to one side, you have to do to the other side. Now, is it okay if I subtract x from both sides right here?
Yeah.
They're going to cancel, right? They're gone. So now if you simplify, you have negative 7 is equal to 49, and I can group these two terms together to give you negative 14 radical x. Now what do? You move the 49 over by subtracting it, which leaves you with negative 56 is equal to negative 14 radical x. And then you do what? Divide by negative 14. So you divide by negative 14, which is what? 4. And then what do you have to do? Square it. And 16 is equal to x. As the final step, what do you got to do? You got to check yourself, right? We got to put it in to check for an extraneous solution. So we come up to the top. What did we say that value was? 16. So if I put it into this equation, what is 16 minus 7? What is 16 minus 7? 9. The square root of 9 is 3 plus the square root of 16, which is 4. Does that equal 7? Yes. Therefore, your answer is x is equal to 16. Well, the part before that, just move it. You move a radical over and square it. One more. Your problem is going to be the square root of, let me change it, y. How about a y? The square root of y minus 27 plus the square root of y equals 9.